Hello, so in this video we're going to look more into differentiating functions, or in other words finding the gradient of a function. Now last time we said if you had a function y is f of x, we saw that the gradient of this function, we don't need to draw tangents anymore. Instead we used this this expression here. So then we said f dash of x, so the dash meaning the gradient function of f, so basically the gradient of our function, okay? And so therefore this was equal to the limit as h tends to 0 of f of x plus h minus f of x over h. So this is the definition of the gradient of a function. So the idea is if we plug in any value of x into my gradient function here, I then get the gradient at the point on the curve, okay? So I don't need to draw tangents anymore. And so we got an algebraic, a proper way of now finding the gradient. However, when there are certain functions where it can be pretty difficult or pretty tiresome to be able to just use this definition every single time, right? So mathematicians then, they were lazy or creative, depends how you look at it. Instead, they tried to find more rules or ways of working out particular gradients of particular functions without having to just use this formula here. So for example, and in this course, let's say we have a function f of x equal to x to the 10 or sine x, or x squared plus 1 over x minus 1, 2 to the power of x. So many different functions, right? We can actually find the gradients or the gradient function of all of these. In other words, we can differentiate these various functions of x to find the gradient function. So then f dash of x would then be, well, we'd have to find a way of finding the gradient function, right? But obviously, the only thing we know so far, if we were to work out the gradient functions of these functions, right? So f of x is here. So then the gradient function f dash of x would have to resort to using this this rule here, okay? This definition. But there are many type of functions, okay? It's very cumbersome, very difficult, very lengthy to have to every single time, if you were to find the gradient, having to use this formula every single time. So mathematicians found different ways, okay? So the first class of functions we're going to look at, and the functions you'll look at in AS, is a function of the form x to the power of n, where we have a power of x, okay? The power n of x, okay? So for example, well, first of all, x to the 10, that's my first example. Or 2x to the power of 30, or even root x. And root x is the power of x, because if you use index laws, that's just x to the half, okay? So as you can see then, there are many different type of functions that, or expressions of x, that fall into this category, where we have x to the power of n. So that's my first type of function I'm going to look at, and again that's what we'll be looking at in AS in year 12. In year 13 we will look at other types of functions to differentiate, okay? But we're going to start off with x to the power of n first of all. So again, this is my function then, f of x is x to the n. Okay, so what's the gradient going to be? What's f dash of x going to be? So again, we're going to then use my first principles, my definition here, okay? So before we get started then, a little preliminary. We are going to need to expand a bracket x plus h to the power of n, right? So I'm going to do that now then. So again, h is just a number, right? H is just a number, really. And n's just a number as well. N's an integer, a positive integer. So how are we going to expand this bracket? We're going to need to expand the bracket. Let me just write out the first. Let me just write out the first step in my differentiation. So f dash of x is the limit as h tends to 0, and then my function is x to the power of n. So it's going to be f of x plus h, right? But f of x plus h. So then f of x is x to the n. So f of x plus h is x plus h to the n. Take away x to the n over h, and so you can see we're going to need to expand this bracket here. How are we going to do that then? We're going to use the binomial expansion, okay? So, x plus h to the power of n, well, let's use the binomial expansion. We looked at this in chapter 8, how to expand brackets like this. So so my first term is going to be x to the power of 0. So my coefficient is going to be n, my power, right, my n, choose 0. Then we're going to have x to the power of 0, then h to the power of n, okay? Then we're going to have n choose 1, and then x to the 1, and then h to the n minus 1, right? Then we're going to have n choose 2, x squared, h to the power of n minus 2. And then hopefully you can see the pattern, right? How we're going to proceed forward. So we're going to continue this pattern, and then eventually we're going to get to n, and then n minus 1, right? And then x will be a power of n minus 1, and h will be a power of 1. Then lastly, we're going to have n choose n, and then x to the power of n, h to the 0. But h to the 0, anything to the power of 0 is just 1, okay? And actually then I can simplify some stuff, because x to the power of 0 is going to be 1 as well. So that's just h to the n here. And x to the 1 here is just x. And likewise h to the 1 is just h, okay? So I'm just simplifying my indices there. So hopefully you can see what I've done there. How I've expanded the bracket using the binomial expansion. Right, okay. Okay, what do I want to say now? Well, actually, what I want to do, I want to factorise a h. Okay, you'll see why I'm going to factorise a h in a moment. But notice every single term here, excluding the final term n x to the n, excluding this term, every other term has a h in it, okay? Hopefully you can see that. So we can factor a h out of everything else. So it's going to be h then. Then we're going to have n choose 0, h to the n minus 1, add n choose 1, x h to the n minus 2, add add n minus 1, x to the n minus 1, and then h is already factored, so that's it. And then I'm going to add on the n x to the n outside, okay? So all I've done here is factorise a h out of all the terms that do have a h in, okay? Right, now, okay. The final thing I want to look at is this bit here, this n choose n, x to the n. Now, n choose n, if we then use this formula here, so in general, n choose r is n factorial over r factorial of n minus r factorial. In this case, when r is equal to n, we get n factorial over n factorial of n minus n factorial. Well, these cancel, and I'm left with 1 over 0 factorial, but 0 factorial is 1 as well. So it's just 1, okay? So we can do we can do a final simplification, and n choose n is just 1. So overall, we just have an x to the n at the end there, okay? Cool. So then I'm going to sort of substitute that in then. So into my gradient here, x plus h to the n is this whole expression here, right? This is f of x plus h, which is x plus h to the n. So it's going to be h lots of n choose 0, h to the n minus 1, add n choose 1, x h to the n minus 2, add dot dot dot, add n minus 1, x to the n minus 1, add x to the n. Okay, so that's x plus h to the n, but then I'm taking away x to the n. Okay, but actually then notice I have a plus x to the n and I'm taking away x to the n. They will cancel each other out, so actually that's it. Okay, then I'm dividing by, I should put my limit outside actually. So it's the limit as h tends to 0, and then this is all divided by h, and now you can see why I wanted to factor a h out of everything that I could. Okay, so if I get rid of this now, hopefully you notice now I can cancel a h out. So now I can divide by h, so it's then going to be limit as h tends to 0 of n choose 0 of h to the n minus 1, add n choose 1 of x to the h n minus 2, add dot dot dot, add the final term n of n choose n minus 1, lots of x to the n minus 1. Okay, now at this point then I'm going to consider making h 0, right? So if I then try what happens when h is 0, well, what happens, every term with h will go to 0, right? Look at this. So this will be n choose 0 of 0 to the power of n minus 1 plus n choose 1 of x lots of 0 to the n minus 2, add dot dot dot, add n of n minus 1 x to the n minus 1 as my final term. Well, the term before it, right, the term before the last term, the second to last term, right, that's going to have a h term in as well, right? So it's going to be n of n minus 2 h x to the n minus 2. Add that, okay? But then this h goes to 0 as well, okay? So actually, what do you spot? Basically, when h goes to 0, every single term except the final term here, that every single term has a 0 in now, because every single term had a h in, but h is 0. So this goes away, all these terms in between go away, and this goes away, because all of that has a 0 in it. So we're left with n of n minus 1, x to the n minus 1. And that's basically it. But there's one final thing. We can actually simplify this coefficient as well of n minus 1. If I go back then to my n choose r formula, we can also see what happens when we have n of n minus 1. Okay? So then it's going to be n factorial over n minus 1 factorial of n minus n minus 1 factorial. But we can firstly simplify this bit, right? We can expand this little inner bracket here, because minus lots of n minus 1 is minus n plus 1, right? And then these cancel out. The n minus n cancels out. So that then leaves me with n factorial over n minus 1 factorial of 1 factorial, okay? Because again, that n minus n cancels each other out, okay? So that goes to 0, so I'm left with 1, okay? Now, actually, and then 1 factorial is just 1, right? So that's nothing either. So I'm left with this, n factorial over n minus 1 factorial, but then remember, n factorial is just a number times by itself down to 1. So it's n times n minus 1 times n minus 2 times dot 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 times 2 times 1. Well, actually, if I then just ignore the n, what about the terms after it? That's just n minus 1 factorial then, right? Hopefully you can see that, because then it's the n minus 1 numbers being times together, times them by n. We can substitute that in. So then it's going to be n lots of n minus 1 factorial over n minus 1 factorial. And then what do you notice? We can cancel that out to be left with n. So that's telling me then n choose n minus 1 is just n. So I can substitute that into my result here to say that this is n x to the n minus 1. And that's it. Okay, I can't do anything more with that. So then that's telling me then, overall, if I go back to my original problem, my f of x was x to the n. That's what I was finding the derivative of. That's what f dash of x here was doing, was finding the derivative of x to the n. That's my function. And then I found that the derivative was n times x to the n minus 1. So therefore the derivative of x to the n here is going to be nx to the n minus 1. And that's it. So it's saying then, effectively, when we have x to the power of n, the rule is that to differentiate from the gradient of it, we can do the power n times by x and then knock 1 off the power. Okay? And so that's it. So now we no longer really need to resort to using the first principles, this whole fraction definition here. We can use this rule instead to differentiate powers of x. Okay, so I'm going to summarize it once more. We can say overall that what should we say, if we have an expression of x, f of x, to be x to the n, then the derivative is f dash of x is equal to nx to the n minus 1. Okay, and that's what we'll be using all throughout year 12, all throughout the first year of the course, but also we'll be using it later on as well from that. So it's a very, very, very powerful rule, and we call this the power rule. Okay, the power rule. Okay, so if we have a power of x, that allows me, if I use this rule, to differentiate that expression there. Okay, so that's probably a lot to take in. I will say you do not need to remember how to derive or work or understand how to differentiate x to the n using first principles. You do not need to learn what I've just done. Okay, the only thing you need to learn is the power rule here, which we will be using now in a second when we're going to look at some examples. So if it's like what's going on, do not freak out. I've only done this to show the backstory, okay, of why we have this formula, okay, for those interested. But this is what we'll be using, okay, and the examples now I'm going to show how to use it, because again it's like, what does this actually mean? I'll show you how to use it now, but that's the backstory, okay, that is the backstory. And one last comment as well, some students may pick up on the fact that n, with this binomial expansion we did, is only for positive integers of n. In year 2, we will be looking at a more general, a more advanced version of the binomial expansion, right? Which works for all powers of n, even if n is negative or fractional. Okay, so we will look at expanding brackets such as x plus 1 to the power of minus a third. Okay, we won't know how to do that in year 1, only positive powers, right? But we can use that formula in the same way as I've done here to also arrive at this at this expression here. We will get the same rule for any power of n. Okay, and so hopefully you get the idea of how we got to that rule. Okay, probably enough waffling now. Let's jump into some examples with this. So I'm going to note it then. If f of x is equal to x to the n, f dash of x is n times x to the n minus 1. Okay, we'll be using that here. So how do we use it then? So we're told to find the derivative f dash of x when f of x equals, first of all, f of x is x to the power of 6. Okay. Well then, f of x is x to the 6. If we look at our formula here, n is 6. What that means is then that the derivative, what we're going to do is bring this power to the front of the expression. So the 6 would go in front, okay? So it's going to be 6x then. And then the power is knocked down by 1 because it's n minus 1. So 6 minus 1 would be 5. And that's it, okay? That's a derivative, okay, of this function here. Okay, part B. We have x to the power of a half, okay? So f of x is now x to the half. Now then, again, the derivative of this then, we're going to bring the power to the front of the, so it's going to be half x, and then the power, you knock 1 off. So it's going to be half minus 1, okay? Well, what's a half minus 1? That's going to be negative a half, okay? A half minus 1 is negative a half, and there we are. Okay, that's my derivative there. Part C, we have x to the power of minus 2. F of x is x to the power of minus 2. So again, we're going to use the rule. We're going to bring the power, which now is minus 2, not just 2, but minus 2. All of that is brought to the front. So it's then going to be, so it's now going to be minus 2, lots of x. And then the power gets knocked down by 1. Now, minus 2 minus 1, that would be minus 3, okay? It wouldn't be minus 1, it'd be minus 3, okay? Because you're knocking 1 off, meaning you're subtracting by 1. So minus 2 subtract 1 would be my new power of minus 3, okay? So that's my derivative there. Part D, we have x squared times x cubed, right? So f of x is x squared times x cubed. Now we can only differentiate or find a gradient of a single power of x. I got 2. How can I bring it into this form here of x as a single power? We can use index laws, right? If we're timesing 2 together like this, we can add the powers. So it's going to be x to the 2 add 3, which is x to the 5. Now we can differentiate this, right? So then the derivative, again, we're going to bring the power to the front, so it's going to be 5x. Then we're going to knock 1 off, so it's going to be 5 minus 1, which is 4. And that's it, it's 5x to the 4 there. Okay, part A. We now have x over x to the 5. Well, again, I only want x as a single power. I have 2 x's here. So I'm going to need to simplify, right? I can use index laws. So again, this is x with a hidden 1, right? So then I can subtract the powers because we're dividing. So it's going to be x1 minus 5. That'll be minus 4, okay? Therefore, my derivative then, my gradient, my f dash of x, if I differentiate, it's going to be minus 4, bring the power to the front, x, and then the new power, you knock 1 off. So minus 4 minus 1 is minus 5, okay? And that is my gradient there. Okay, so hopefully you're starting to get the idea of how we can use this rule. It's a lot easier to use than it looks, right? You just bring the power to the front, so x to the n becomes nx, and then we knock 1 off, so subtract by 1. Okay, we're going to look at some more examples. Now, 2 things to note. First of all, if we have a coefficient, a number in front, so if f of x equals ax to the n, so if we have a coefficient, a number a in front of my x to the power of n, we can basically just ignore it. So then if we differentiate in the normal way, well, if we ignored a and we just differentiate x to the n in the way that we just did, we would again bring the power to the front, so it's going to be n, x to the n minus 1, and then the a at the end. The a remains in front, okay? We don't do anything to the a, we can just leave it where it is, and then we just focus on differentiating the power part of x. So that's the first thing to know. If you have a number in front, that's completely fine. We still differentiate the actual power of x. The second thing to know is we use this notation f dash of x, right, for the derivative. We can also use dy dx, okay, and that means the same thing, okay. Dy dx, f dash of x, they're both gradients of x. They're both gradients or derivatives, okay. They're both exactly the same thing, just different ways of expressing the gradient, okay. You may also use, especially mechanics, there's a third, I'll make a note of it actually, so f dash of x, dy dx, and there's a third notation you might see as well, especially mechanics, and it's y dot, with a dot in the front, on top of it in the middle there, y dot. All these three bits of notation are the same thing, okay? They are equal to the derivative. Okay, so there are three different ways of expressing the derivative of something, okay? So you'd have f dash of x, dy dx, or this y dot above it, okay? We don't use this third notation usually. It's usually these two you will see. But you need to know, if you see these two symbols, f dash of x or dy dx, they're referring to the derivative. Okay, we clarified that then. Let's have a look at this example. We have dy dx then, so again the derivative, where y equals, first of all, y is equal to 7x to the power of 3, where we have a number 7 in front. But needn't worry, because we just leave the 7 where it is. So then if we differentiate, if we find dy dx, we have a 7, we leave the 7 where it is, then we differentiate the x cubed part. Well, x cubed, well then we bring the power 3 to the front, so it's going to be times 3, actually I should use a bracket, right, 3x and then we knock 1 off the power, so 3 minus 1, which is 2, okay, so 3x squared is the derivative, but then overall, because basically we're timesing everything by 7, we can do 7 times 3, and overall that's 21x squared, and that's my final derivative, okay. Part B then, we have minus y is equal to minus 4x to the half, well again, for our derivative, we're going to leave the minus 4 where it is in front, and then we differentiate x to the half, so we're going to bring that half to the front, so times by half x, then we knock 1 off, so a half minus 1, that would be minus a half if we do that, okay? Cool. Then, lastly, we can expand this bracket, right? And then do minus 4 times a half, that's minus 2, x to the minus a half. And there we are, okay? Part C, we then have 3x to the minus 2, so then dy dx is going to be 3. Then if we differentiate the x to the minus 2, that would be minus 2, bring the minus 2 in front, x, and then minus 2 minus 1 is a minus 3. Okay, and then lastly we can expand the bracket to simplify. 3 times minus 2 is minus 6, x to the minus 3. And there we are. Part D, we now have the expression 8x to the 7 over over 3x, okay, 8x to the 7 over 3x. Well, again, at this point we're going to need to use some index laws, because we have two different x's, right? We need a single power of x. So how are we going to do that? Well, firstly, we can deal with the physical numbers first. So it's 8 over 3, and then we deal with the x's. So then x to the 7 over x, well, again, x is just x to the power of 1. And then we can subtract the powers. So it's then going to be x to the 7 minus 1, which is 6. Okay? Again, remember your index laws. We can simplify in this way. So that's my simplified expression. But now we can recognise it's just a single power of x, which I can differentiate. So then if I differentiate it, I'm going to leave the 8/3 outside where it is, and then differentiate x to the 6. So the 6 comes in front, x and then knock 1 off the power, which is then 5, okay? And then finally, if we simplify, 8/3 times 6 would be 16 x to the 5, okay? And that's my final answer for the derivative. Okay, part E, we lastly have root 36 x cubed. Okay, well again, it's not really written in the form, you know, x to the power of n, right? I have this square root outside. I'm going to need to use index laws to deal with that, okay? To bring it as a power of x. Okay, well actually, we can actually then, well, you can look at this two ways. You can recognise that this is a sort of surd, and we can split up surds, right? In this way, so we could split this up to root 36 times root x cubed, okay? And then root 36 actually simplifies to just 6. So root 36 is 6. So we have 6 times root x cubed. Well, actually then we can actually rewrite this as just a power. Because remember, anything rooted, remember root a is just a to the half, right? Remember, a power of a half is the root, okay? So then we can say that's 6 lots of x of x cubed, all raised to the power of a half. And then we can times the powers together, because then it's going to be 6x to the 3/2. And now we're in a position where we can differentiate, because now we just have a power of x in this way, okay? Alternatively, I did say another way, instead of using that to split up the root, instead you may realise we could say the overall, right, the overall 36x to the x cubed is all square rooted, and then we can raise everything to a power of a half. Then we can split up the power of a half to be 36 to the half, x cubed to the half. And then 36 to the half, again, is just root 36, which is 6x then, and then x to the 3, the powers times again, so 3 times a half is 3/2, and then you get the same expression, okay? It just depends how comfortable you are, which method suits you, but you do need to remember your power laws, because often they're not going to be that nice about just giving you something pre-prepared to differentiate. You might need to do some simplification before you're able to differentiate in this way, okay? So you must know your index laws and be comfortable, okay? We did that in chapter 1, okay? So if you need to have a refresher on those index laws to understand why, we can go and start from here, from root 36x cubed to 6x to the 3/2. If you're not comfortable with what I did here, you do need to revise that and recap that. Okay, so we're in this, we got to this point, then the derivative, at this point we can just then leave the 6 out in front, then we differentiate x to the 3/2. So then we're going to bring that power to the front, so 3/2x, and then we knock 1 off, so 3/2 minus 1, that will go to a half, okay? And there we are. And then finally we can expand the bracket by timesing 6 with 3/2. That would be 9, okay? 9x to the half. And that's it. Okay, cool. So hopefully you're getting a sort of good idea now of how we can use the power law, right, to differentiate powers of x in this way. Okay, and that's really what we'll be using in this section. It won't get any more complicated than that. In year 2 we will look at more different types of functions of x we can differentiate, but for now this is basically all there is to it, okay, for year 1 at least anyway. So make sure you're comfortable with what we've done here, but we're going to look at one final example. We're told that 2y squared minus x cubed is equal to 0. We need to find dy dx. Okay. Well, the thing is, if we're going to find dy dx, we first need y on its own equal to f of x, right? I need y equal to to some expression of x. The problem I have here is I have 2y squared. I don't have y here. I need to sort of rearrange then to get y only, not 2y squared. So, okay, let's rearrange then for y. Right, so then 2y squared is equal to x cubed by adding x cubed. Then we can divide by 2 to then get y squared is x cubed over 2. And then I need to square root, okay, to get from y squared to y. Y is then going to be the root of x cubed over 2. Now, obviously you might be thinking plus or minus. We're not really solving for an equation, but we're not solving to find roots or solutions. We're just finding an expression. It's like, for example, how root 4 would equal 2. But you wouldn't say that root 4 would equal minus 2. That would be wrong, okay? But what you would say then is that x squared equals 4, then x would be 2 or minus 2, okay? So notice again the key difference is this is evaluating. This is only evaluating a root in the first example, and this is solving, okay? So when we're just literally trying to root something, we're not finding solutions, then we don't need plus or minus, okay? Okay, so in this case it's just plus. And actually that makes sense because they even told us that y has to be positive. Y is greater than 0. If we had minus, that wouldn't make sense because then y would be negative, and that violates what the question said. Anyway, just thought to go over that. So this is my final expression for y, but then they want me to find dy dx. Well, again, it's not really then. This function of x, this root x cubed over 2, isn't a nice power of x. I need to use index laws to simplify. So then again, I can split the root up to both top and bottom, right? So it's going to be root x cubed over root 2. Right. And then I can use power laws to simplify root x cubed, because that's going to be x cubed to the power of a half. And then I can do the same for 2 to the half, okay? Then this will go to x to the 3 over 2 if I times the powers, right, over 2 to the half. I can't really do much to this 2 to the half. Actually, I'll tell you what we could do. We could leave it as root 2, then we can rationalise. Then we can times by root 2 over root 2 to then get root 2 over 2, lots of x to the 3 over 2. Okay, slightly nicer form to work with. So we got this. So we got this final expression of x. Again, we have this whole fraction is just a number, right? So it's a coefficient of x to the 3 over 2. We can now differentiate. Okay, right. So then if we differentiate, again we leave the number in front, root 2 over 2 where it is. Then we differentiate the power part of x. So we're going to bring the 3 over 2 forward. Then x to the 3 over 2, knock 1 off the power. Then we can expand, right, the bracket by doing root 2 over 2 times 3 over 2. That would be 3 root 2 over 4, okay, times by x to the half, okay. 3 over 2 minus 1 is a half there, okay. And there we are. So that's my derivative. Okay, so that is a sort of brief introduction to differentiating powers of x. Okay, like I said, if the intro was confusing about how we got to the power rule, how we got to differentiating it with the first principles, that's fine. You don't need to get that. It's just for those interested. But what you do need to know is how we can use the power rule to differentiate powers of x, okay, and how we can use index laws to simplify equations in order for us to be able to differentiate, okay. Okay, so I'll leave that there. I'll see you next time.